Hello everybody, my name is Ho Kyung Sean at University of Technology Sydney. This is my great pleasure to be part of the first international conference on ACE forensic engineering. First of all, I'd like to thank you, Professor Hong and the organizing committee to give me opportunity to present my research activity. Today, my talk is about the future of electro-membrane processes. I will begin with the background on the electro-membrane processes, and especially I want to focus on the CDI, MCDI, capacitive deionization, membrane capacitive deionization application and technology, and try to highlight of MCDI research in UTS, and then what would be the future of MCDI and the research gaps, and then I will finish my presentation. Electromembrane processes utilize the electrical potential gradient as the driving force of the ion transport. So the main electromembrane process are electrodeionization, electrodialysis reversal, electrodialysis with bipolar membrane, electrodialysis, and capacitive deionization. So they consist of electrodes, anionic cationic membranes, and then they have some of the power generation. And this is the very much conventional electrodialysis diagram. So you can see the plus charge, minus charge electrodes, which called anode and cathode. And you need the cationic anionic membrane, and then you have a channel for the diluted solution and then concentrate solution. So you can see this dilute solution pass through these two channels, and concentrate solution pass through. You have different ions can pass through the only anionic membrane or cationic membrane, and then you can dilute your channel, and then you can concentrate. So that's the very much a typical electrodialysis. And the EDI consists of same as electrodialysis. Difference is the ion exchange region. So different cation anion region consist of in this channel, and then this feed water is flowing and then absorbed by different ion on the different region, and then they can stay in the region and then slowly move through their electrical forces, and then goes to the anionic membrane, cationic membrane, and then you can concentrate your ion. So this one called the EDI. And also we have a selectrodialysis. So what's the difference will be selectrodialysis utilized a little bit of different membrane structure, and typically anionic cationic membrane in electrodialysis. However, in selectrodialysis, we use the monovalent anionic membrane, and then we can let the different anion can pass through from this monovalent anion exchange membrane. Just typical anion exchange membrane. For example, we have chloride and then sulfate ion, and this monovalent ion can pass through the anion exchange membrane as well as the monovalent anion exchange membrane to create some bright and productive water. However, sulfate ions. So divalent ion can pass through the anion exchange membrane, however, cannot pass through this monovalent anion exchange membrane. So you can collect very much selective your ion using this electrodialysis membrane processes. Also, we have bipolar membrane, and you can see this bipolar membrane consists of different bipolar membrane, plus charge, minus charge, and then this will concentrate your H plus and then hydroxy ion, and you will collect your sodium from this cation ion, and you have chloride ion from the anion exchange membrane, so you can collect HCl and sodium hydroxide. So this bipolar membrane can produce your sodium hydroxide HCl from your salty water of the sodium chloride. So this is the very easy way to produce your caustic material and then acidic compounds. If you look at the global top 10 players, GC, BWT, DuPont Water Solution, BWRO Water Technology. Also, we have Fujifilm and Sunopure and Seawater Technology. So they represent just the empty circle is about the small player, and then this active market and major market player. So you can see the only market player. So BWRO Water Solution very much focus on the EDI technology, and then Seawater Technology very much focus on EDR. EDR is the electrodialysis reversal, which means they try to change the polarity, so make sure that their cleaning as well as some of the fouling issue can be reduced by this EDR technology. Also, they have relatively very high water recovery compared to the electrodialysis because they are reversing the polarity. So different companies focusing on different their own electro-membrane process development. Also, you can see the ion exchange membrane development company, how they are working to contribute this electro-membrane processes. Also, they have different resin application. So you can see what's the years. We are now in 2022. So how much they are spending for this electro-membrane processes. So you can see the East Asia Pacific area has highest spending of the electrochemical processes, followed by the North America and Europe. So they keep growing their application of electro-membrane separation. Also, you can see the application where is the most suitable place to apply electrochemical processes. You can see the ultra pure water treatment is one of the very much reliable this electrochemical process, followed by wastewater treatment and process drinking water treatment process. So more specifically, which industrial area can be applied. So you can see the microelectronics are the highest spending of this electro-membrane processes, followed by the pharmaceuticals, which are the high-valued material. So microelectronics, such as semiconductor or pharmaceuticals, and then you can also apply it to the different specific industrial areas. So overall, the electro-membrane processes has pros and cons. So the advantages are high efficiency of the separation of substances without phase transitions. Especially, they can also make happen to selectively separate your ion, as I mentioned, the sulfate and chloride. So you can try to utilize some monovalent anionic membrane. Also, you can use the bipolar membrane to have a specific application of electrochemical process and easy continuation optimization, low demands for space, and lower energy consumption compared to traditional procedures, and possibility to create the closed waste-free technology junctions or entire technology. Of course, every technology has a disadvantage. So this electrochemical process have disadvantage of membrane fouling, the creation of the coating of a poorly soluble substance on the membrane surface. So that we need to also try to develop how to improve the overall fouling mitigation. And that's the general agenda of electro-membrane processes. Today, my main talk is about CDI because still CDI is the emerging compared to the electrodialysis. We have to go for the commercialization more actively, so that I have selected this one as the main topic of the today presentation. So CDI consists of same as electrochemical processes. So we have porous carbon electrodes in the water channel, and then porous carbon electrodes, and then graphite. So you have a connection of your current, electrical current. And CDI is emerging desalination technology, highly suitable for low saline water, a relatively fast process for desalination and electro-regeneration, efficient removal of charged ions, ideal technology for decentralized and then small-scale system with the solar or the wind energy. So why the CDI does not have mass market adoption? Because still this is the emerging technology. Only a handful of technologies apply around the world, and then limited number of case studies of practical application. That's the reason why it's still growing technology. If you look at the maturity index, it's time. So ED and RO, so CDI is just about to go for the exponential phase, so that there are only limited number of industry organization. Siontech from Korea, Voltia from Netherlands, Atlas Technology, US, EST from China, and Indropan Dello Pro from Italy. And this is the mechanism of this membrane CDI. So you have graphite, carbon electrodes, and cation exchange membrane, anion exchange membrane, carbon electrode, and then graphite. So this first you need to have adsorption. So this is the low pressure technology, low voltage, less than 1 volt, and then chemical process, and focus on the aspects. So water is coming, plus minus charge with the different salt, and then you just produce your electrical force, and then cationic can be observed on your carbon electrodes, and the anionic can be observed on your carbon electrodes, and then you can just separate your ion And this next step will be desorption. So once you observe, and then you can try to make desorption. So you can see the different polarity can be applied, or just make shut down the electrical pole. And this is also possible to make energy recovery. Also can be focused on the resource recovery system. So what are the limitations of current technology? So energy intensive for this desalination, for such as reverse osmosis, and the high capital cost, and the slow kinetics, limited capacity and chemical use, and then energy intensive, impractical to scale up. So that we believe MCDI can be one of the very high potential of the future desalination in a certain niche market, and energy efficient, low cost, the easy operation and chemical free process can be achieved from this technology. So what's the research progress at this moment? So electrodes. So a lot of people are very much focused on the electrode to develop the best electrode material. The carbon activate, carbon aerosol, and then graphene, and the carbon nanotube. At this stage, carbon activate carbon is the most widely used electrode, because this is the relatively cheap and then very high the surface area, which is almost 2000 square meter per gram. So other materials very much useful, but still the cost is very high. That's the reason why the most of commercial electrode are used for activate carbon. And then application 20%, process development 18%, energy 6% of the CDI research, and mostly they are targeting on the brackish water, water softening, and heavy metal removal. For example, like you need to remove arsenic, or you need to remove some nitrate in your groundwater to produce the drinking water. So you don't have to remove all the iron, which is the very good mineral for human body. So calcium, magnesium, you don't have to remove in your groundwater system, but you need to remove some of arsenic or nitrate. So in this case, so you can apply for CDI specifically. We can also remove the some of the target compounds. Also improving the energy sustainability in MCDI was due to the low energy intensity for MCDI. So solar energy can be used to power a decentralized MCDI system in remote places. So that's the one of the merit to apply. So let us compare the energy consumption of RO and MCDI. So this is the energy consumption in terms of kilowatt hour per cubic meters, and this is the salt concentration from 1 to 7 gram per liter. So if you look at the reverse osmosis, so when you have 5 gram per liter, so they are very much consistent around 0.5 kilowatt hour per cubic meter. So when you have seawater concentration, which is 35 gram per liter of TDS concentration, so you need around 2 kilowatt hour per cubic meter here. When you have 35 gram per liter of your salt concentration. On the other hand, the MCDI is very much straightforward. So when you have less concentration, such as less than 2000 milligram per liter or 2 gram per liter. So this MCDI compared to the reverse osmosis technology. So they are very much low energy consumption. So in a low salinity, so it has merit to remove your salt concentration using the MCDI technology compared to the reverse. We have published a lot of papers on MCDI through the COREP project. We have developed bromide removal for desalination. Also, we have focused on the resource recovery and for the value of metal or nutrient recovery system. So today, just want to focus on the one of our main research direction based on the COREP project. So seawater desalination, how to utilize our MCDI. So seawater has 35 gram per liter of salt, 75 milligram per liter of bromide. So in Australia, we are a little bit focused on the bromide rather than boron concentration, because most of desalinated water mixed with the fresh water, such as the dam water or groundwater, so that relatively our boron concentration is low. So we don't have much boron issue at this moment, but bromide is carcinogenic compound, so that we try to remove this compound. So after pass of the reverse osmosis, we have 100 milligram per liter of salt, 1 milligram per liter of the bromide, still very high concentration of the bromide as well as the TDS. And second pass reduced significantly your TDS concentration, 10 milligram per liter, was 0.1 milligram per liter of bromide concentration. And that's very much we are utilizing this second pass to remove the bromide less than 100 microgram per liter. So if we replace this second pass with CDI, whether we can have more energy saving and easy to operate this reverse osmosis. So why we are targeting on the bromide? So this is the natural salt, non-toxic, so not regulated, potential source of the DBP, disinfection byproduct during the water disinfection guideline value for desalination Australia, less than 100 microgram per liter. So bromide combined with the chlorine ozonation or chloramine, you produce the HOVR, and then combined with the NOM or ozone, so you will create some of the very harmful carcinogenic compounds of the DBP or bromide O3 compounds for your disinfection byproduct. So that we try to remove this bromide for the lab scale. We utilize the adsorption, and then 0.1 voltage flow rate is 45 milliliter per minute. And then we tested what's the TDS removal and bromide removal. So 100 gram per liter of your TDS, and then 400 gram per liter. So when you have your high concentration of TDS, so you reduce your overall bromide removal up to 45% from almost 99% of your bromide TDS. Also, we compare with the energy consumption between brackish water, reverse osmosis, and MCDI. As I mentioned, we have used the second pass RO, which called the BWRO, in a seawater desalination plant. So we're targeting on the post desalination plant, second pass. We utilize the energy consumption for RO, 85% recovery, almost 0.35 kilowatt hour per cubic meter. And then when you use the MCDI, so when you have your TDS concentration 100.05 kilowatt hour per cubic meter, and then 400 milligram per liter, 0.3 kilowatt hour per cubic meter, so that the MCDI is more energy efficient. Just 30% of the BWRO for feed TDS 200 milligram per liter can be achieved using the MCDI technology. Also, we tested a pilot MCDI unit for bromide removal, and this is the result of effect of low desorption flow rate. So TDS of the treated water desorption flow rate, it doesn't really make a very big impact of the overall TDS concentration. And then removal also very much consistent. 70% of the bromide TDS is almost 96%. Also, we look at the energy use at the lower desorption rate, and they have also very much similar 0.15 kilowatt hour per cubic meter to 1.6. So definitely it reduced the overall energy consumption at the low desorption flow rate. And to improve overall selectivity of the bromide, so we have developed the bromide selective electrodes. So this is the bromide resin, and then we mixed with our anionic exchange membrane polymer, and then this bromide selective resin powder and the anion exchange membrane polymer mixed together to produce our ion exchange membrane. And then we tested what's the overall selectivity of bromide ion. So we try to look at the conductivity, how they change with time. So different sodium chloride and then sodium bromide, and then how this electrostability has different behavior. And then we have found out that they are almost a similar way of the very much stable condition. And then we look at the detailed bromide adsorption in binary solution. So this is the MCDI and bromide resin MCDI, and this is the typical MCDI and the bromide resin combined the MCDI. So you can see the red circle and then purple triangle. So absorption capacity increased when you have more bromide ion exchange membrane. So you have almost 3.4 times higher bromide removal. On the other hand, if you look at the chloride concentration, so your bromide resin has less chloride absorption capacity. So which means this bromide resin membrane works very well to have a better selectivity of the bromide with the 3.4 times compared to the very much typical MCDI technology. And this is the mixed anions. This time we compare with the different anions: chloride, bromide, sulfate, phosphate, nitrate, iodide. And then you can see the bromide, your MCDI and then bromide MCDI. So you have a very much higher removal of bromide MCDI, 79%, but on the other hand, just the normal MCDI only 8%. So when you have different also sulfate and then mixed anion, also we have found our bromide selectivity was almost 10 times higher than other anionic compound. So we have successfully developed how to improve the overall targeted selectivity using our anion exchange membrane. So I could conclude from our previous study, MCDI could replace the second pass BWRO in seawater desalination, so that we can reduce our energy consumption almost 30%. So post-desalination plant BWR required 0.35 kilowatt per cubic meter, but when you use the MCDI, so we can use almost less than 0.2 kilowatt per cubic meter. MCDI is energy efficient for desalination of low TDS water. MCDI can be used for selective removal and recovery of target compound, coating with the ion selective resin. So that's one of the advantages we can apply for MCDI, the anion exchange or cation exchange membrane in the future for high selectivity. In the future also we can improve the more focus on the practical energy recovery. Also novel electrodes development can be also developed, and then potential application for MCDI in target ion removal, also coupling with some of linear energy will accelerate this MCDI technology for next couple of decades. So this is the project correct with Professor Hong, and then he has installed this pilot demonstration 1000 cubic meter per day, and then this low energy seawater desalination we have demonstrated our MCDI with the capacity of the 50 cubic meter per day, and then Jung Hyun and then Professor Hong have successfully operated for last couple of months, and then this project will be very much valuable for the MCDI application as well as the overall low energy consumption for the UAE pilot demonstration. This is our pilot demonstration with the MCDI together with the United Nations Development Program. There is the small Pacific island, which is Tuvalu, very much small area, 25 square kilometer, 10,000 population, and then no fresh water. And due to climate change, the seawater level rise increases, and the salt concentration of the groundwater is also problematic, so that we have proposed off-grid solar power CDI desalination demonstration project with Tuvalu government. And then this is the last year November we had the UN climate change conference in UK, and then this is the Minister of the Environment in Tuvalu. So they try to appeal for the sinking their country because of the climate change, and then we have developed some off-grid solar power system, and then demonstrate the seawater desalination, especially groundwater. We try to work together with them. So this year we have remote control of this MCDI technology to make drinking water for this island. Also, you know that the Tonga is the one of the very much problematic situation at this month because of the volcano eruption. So very recently, a couple of weeks, we had the tsunami in Japan and California because of the volcano eruption in Tonga. So that they also need a lot of support for the drinking water system. Hopefully, we will try to have a more decentralized desalination MCDI unit for the help of this kind of Pacific island. I'd like to thank you, Korea, for this support of our MCDI project for last 5 years. Also, thank you to the United Nations Development Program. Also, Seawater has worked with us to install our pilot unit. And last but not least, we have Lunar New Year next week. So this year is the White Tiger. I wish you a happy and healthy and prosperous New Year for 2022. Thank you for your attention.